In this section, we want to look at galvanic cells. Essentially, this is a way to allow the electrons that are transferred from in a redox reaction to do something useful. And in this case, they're generating a voltage of 0.46 volts. In the next section, we'll talk about how to calculate the number of volts that different cells would be able to generate. But here, what you'll notice is we have the exact same reaction that we had before. We had copper solid plus 2Ag plus yields Cu2 plus Ag solid. And when we mixed all these things together in one tube, all right, namely the copper and the 2Ag plus, what we got was a precipitation of silver. And although there was a transfer of electrons, they weren't doing anything like making a light bulb turn on or something that a battery would do. In this case, we can actually separate the two half reactions, which allows us to make this work like a battery. So you'll notice here that we have copper metal, and it's in a solution of copper ions. We also have silver metal, this piece of silver metal, in a solution of silver ions. Specifically, we have 1 molar copper 2 nitrate for the copper ions, and we have 1 molar silver nitrate for the silver ions. We also have this weird thing called the salt bridge, which is allowing ions to transfer back and forth, so there's no net buildup of charge, which would make this thing stop working. And we also have a wire connecting these. So what's going on here? Well, what we talked about before is copper is going from 0 to 2 plus. This means it's losing electrons, or electrons are a product. So this copper metal is forming into copper 2 plus. When it forms into copper 2 plus, that copper 2 plus goes into solution, and then the counterions are coming from this salt bridge. But basically, what's happening is we're generating electrons. And those electrons can flow through this wire because what's going on the other side? On the other side, we have silver 2 plus in this solution forming into silver metal. So the silver plus in solution is depositing and making this silver rod actually larger, okay, because it's going to have more silver metal on it. And when they do that, they're collecting those electrons. So on this side, we're releasing electrons. On this side, we're collecting those electrons. And the electrons are flowing from this negative terminal to this positive terminal. So there's a couple of things. This is the exact same picture and just the reaction again. There's a couple things to note. The anode, okay, is the negative side. So anode, like anion, is negative. The cathode, like cation, is positive. Well, what's happening at the anode or the negative side? Oxidation. Oxidation occurs at the anode. Said another way, copper metal becomes copper 2 plus 2 electrons. Those 2 electrons occur at the anode, which we consider as negatively charged because there's a buildup of electrons, which are the product of this half reaction. Copper yields copper 2 plus 2 electrons. At the cathode, or the positive end, we're using up those 2 electrons. And when what are we using those electrons for? We're using those electrons to turn silver plus into silver metal. Said another way, at the cathode, reduction occurs. The salt bridge is a U-shaped tube containing strong electrolyte, and it allows the charge to be balanced because the copper 2 plus needs NO3 minus to balance out. And this needs to be able to get rid of some of the nitrate. As the silver pluses go here, the nitrates need to be able to go here, and you can consider them to be interacting with the sodium ions, or you could just think about it as balancing out the charge, if you will, so that you don't get a buildup on one side. If you get a buildup, it doesn't really work that way. It just stops working, okay? So said another way, if you didn't have the salt bridge, this would not transfer electrons for very long. So a couple things to notice here. All right, we are measuring these this current in volts. All right, we're actually measuring a voltage, not a current. So a volt is a joule per coulomb. But this isn't a physics class, so we're not going to talk a lot about voltage in scientific terms. Voltage, put simply, is how strongly electricity is being pushed through the circuit. Another way of saying this is voltage is electrical pressure. So you can think of the anode as like a high pressure region and the cathode as like a low pressure region, and the electrons are flowing from a high pressure region to a low pressure region. It's not exactly pressure, right? It's voltage, but it's the similar idea to how pressure would work as well. Note that the voltage is a physical limitation of the chemicals involved in generating said voltage. And in the next section, we'll talk about the specific amount of voltage that different types of oxidation and reduction reactions can generate. Specifically, we'll look at standard reduction potentials. The other thing to note is that the electrons are flowing from the anode, in this case through a light bulb, to the cathode. Why? Because at the anode, we have oxidation occurring, or electrons are the products, and those electrons are flowing to the cathode, where they're the reactants to, in this case, that we gave here, turn silver plus into silver at the cathode. Note that for some engineering applications, or electrical type applications, they think of current flowing in the opposite direction. I'm not sure that this really matters, and I don't know a ton about it, but essentially you can think about a positive charge as flowing in the opposite direction of a negative charge, which is why sometimes for some applications, they think of the current flow as actually in the opposite direction. But the direction of the electron flow is from anode to cathode, and voltage is essentially an electrical pressure. So at the anode, you have a high pressure of electrons, if you will, and at the cathode, you have a low pressure of electrons. It's not the same as air pressure, but it behaves similarly to it, so that's why we think about it in that way. So let's look at one other type of information in this relatively short section, which is just basically how we notate this stuff, or notation. So if we look here we have magnesium in a solution of Mg2+. All right, the Mg metal is losing electrons to form more Mg2+ and two electrons over here on the oxidation or the anode side. On the cathode side, what's happening? Well, we have HCl solution, and it's bubbling out hydrogen gas. And here we have a non-reactive platinum wire as just a way to transfer these electrons, and it won't react with hydrochloric acid. So we have H+ gaining two electrons and forming hydrogen gas, which is bubbled out, and we again have a salt bridge. In this case, the anode side, I'm not sure why I didn't put cathode side over here. The anode side is the Mg forming Mg2+, and the cathode side is 2H+ plus two electrons forming hydrogen gas. We could write this as a chemical reaction. All right, Mg solid plus 2H plus aqueous yields Mg2+ plus hydrogen gas. But we could also write it as a cell notation, which is the anode side, Mg, with a line, Mg2+, because Mg is forming Mg2+, a double line for the salt bridge, and then over here we have H+ forming H2, and then we're telling people that there is a platinum electrode. Let's look at an example, the same example that we've been doing, okay, with the copper and the silver. So essentially, how we want to have this is as anode, two lines for the salt bridge, and then cathode. All right, so this is basically what we want to have. Remember that the anode is where oxidation is occurring, and the cathode is where reduction is occurring. Note that that's also how this cell is set up. All right, we have the copper anode side on the left and the silver cathode side on the right. So we're just going to write it in this way. Well, what's happening on the anode oxidation side? Copper solid is forming copper 2+ aqueous. All right, and then we have a salt bridge. And what do we have on the other side? We have 2Ag plus aqueous forming 2Ag solid. Now, whether or not you include the stoichiometric coefficients, I think is a matter of opinion, because I've also seen this as Cu solid yields and Cu2+ aqueous, Ag+ aqueous, and Ag solid. I'm not sure if there's one of these that's correct and one of them that's wrong. But what is correct is that we're going to have the anode or the oxidation side on the left, 2 lines for the salt bridge, and the cathode and the reduction side on the right. Here, copper is forming copper 2+ and 2 electrons. This is occurring at the anode. Those 2 electrons are what's building up this negative charge. And then at the cathode side, those 2 electrons are flowing over here, and they're being used to make silver plus into silver. Whether it's 2 silver plus into 2 silver or just silver plus into silver, I'm not real sure on that one. And this isn't the kind of thing where, you know, if you had a multiple choice test, you'd get this answer and you'd get this answer and you have to decide which is correct. The kind of things that they'll do wrong is they'll put copper with silver plus, or they'll put, they'll put this on the left side and this on the right side, this kind of thing. In the next section, what we're going to look at is how do we actually calculate these voltages using standard cell potentials.